Did you feel the earth whisper or rumble beneath your feet? On the morning of November 9th, 2025, a flurry of tremors shook the quiet hills east of San Francisco, raising new questions about the Bay Area's restless geology. What could trigger dozens of small earthquakes almost in unison? Are these minor quakes harbingers of a larger rupture, or merely the crust sighing and settling? In the span of less than a day, 37 recorded quakes struck around San Ramon in Contra Costa County, California. The sequence began on November 9th, at around 10:38 in the morning local time, with a magnitude 3.8, Temblor about 4 kilometers, 2.5 miles, southeast of San Ramon, at roughly 9 kilometers depth. That event was followed immediately by another magnitude 3.7 quake just 55 seconds later, and dozens more, mostly smaller, rolled through the same area over the ensuing hours and overnight. Each quake occurred in the shallow crust of the Calaveras fault system, approximately 8 to 9 kilometers below the surface, and none on its own was especially large. Yet together they form a swarm unprecedented in recent memory for this part of the Bay Area. Seismologists have taken notice. Are these clusters commonplace here, or are we witnessing something unusual? And what do dozens of little shakes tell us about the hidden stresses underground? To unpack what happened, we need to understand the unique nature of earthquake swarms. Most people think of earthquakes as a single large shock, followed by aftershocks that taper off. A major quake rattles the ground first. Then a series of smaller quakes gradually dwindle in size and number. In contrast, an earthquake swarm is a cluster of many quakes of similar size, without one standout main event. The East Bay swarms typically involve dozens or even hundreds of quakes closely spaced in time and location, but none much larger than the others. UC Berkeley seismologists explain that in a swarm, the quake's magnitudes do not decay over time the way aftershocks do. In other words, there isn't a clear big one followed by smaller ones. Instead, the shaking levels stay roughly constant throughout the sequence. When a swarm peters out, it can stop abruptly, almost without warning, rather than fading away gradually. In technical terms, swarms are not dominated by one rupture unzipping the fault. They are a more diffuse or complex release of strain. This Bay Area swarm fit that pattern. The sequence had multiple shocks around magnitude 3, without any single quake orders of magnitude above the others. Swarms are relatively rare on Bay Area faults. Outside of volcanic regions like the Geysers or Long Valley, the San Ramon Valley just west of Mount Diablo is virtually the only place in Northern California where such swarms occur. In fact, Berkeley scientists have mapped at least 10 major swarms in this corridor over the past 5 decades, the latest being the present episode. Many swarms have centered under Danville and Alamo, including a famous 5-week-long swarm in late 2015, with over 4,000 microquakes. The current swarm isn't as large, but it shares the same root cause, a unique blend of tectonic forces and fault geometry in the San Ramon Valley. As seismologists put it, this area is a step over between faults, where stresses transfer from one fault zone to another. Specifically, the Calaveras fault here steps over to intersect with the Concord Green Valley and Mount Diablo fault zones. In such a step-over region, the ruptures are not confined to one planar fault. Instead, deep fracture planes in various orientations can activate, often influenced by fluids or changing stress fields. In plain language, water, rock and pressure. deep underground, form. A complex network of cracks and swarms can occur when that network adjusts bit by bit rather than snapping at one big fault line. What triggered this particular swarm? It appears to be part of the routine breathing of this fault network under constant strain. The San Ramon Valley is under the strong influence of the Pacific North American plate boundary, and the Calaveras fault is one of the main players. Like the nearby San Andreas and Hayward faults, the Calaveras fault is a right lateral strike, slip fault. Imagine the land on one side of the fault sliding horizontally past the other to a right-hand observer. The opposite side moves right. The Pacific plate is moving northwest relative to the North American plate, and that motion is partly accommodated by slipping on the Calaveras fault. But the Calaveras fault is not a uniform, unbroken line. Geologists divide it into segments with different behaviors. A USGS tectonic summary based on the Working Group on California Earthquake Probabilities notes that the fault was divided into 3 segments for hazard analysis. The southern segment, south of where it crosses the Hayward Fault, creeps at about 15 millimeters per year, roughly 0.6 of an inch. It is slipping steadily and relatively fast. North of that, towards its junction with the Hayward Fault, the fault creeps a bit less, around 6 millimeters per year, or 1/4 inch, near the junction. Creeping means the fault is sliding slowly without producing big earthquakes. Creep itself can generate minor seismic activity, but it also steadily relieves stress. In fact, the central segment of the Calaveras fault is so dominated by creep that the USGS notes the fault creeps about 15 millimeters per year in total, matching the slip that must be accommodated by all deformation there. The northernmost part of the Calaveras fault towards Sunol and Danville is quite different. That section is described as virtually locked, with very slow creep of only 2 to 3 millimeters per year. It has very little small quake activity, so very little stress release, implying that strain is building up there over centuries. The last known surface rupturing earthquake on that northern segment was possibly over 300 years ago, and geology studies suggest big ruptures on that part recur on the order of hundreds of years. In other words, it is overdue for a large quake, but it releases strain mostly in tiny steps, or creeps for now. The swarm's location near San Ramon sits in the transition between these behaviors. It is just north of the creeping central zone, in the area where the Calaveras fault starts to fade into a jumble of smaller structures. Because part of the fault is creeping almost as fast as it slips, scientists believe this segment cannot easily produce a quake much larger than those already seen. As one USGS report summarized, because its rate of creep nearly matches the total fault slip rate, it is widely believed that this segment of the fault is not capable of an earthquake having a magnitude much larger than the 1984 Morgan Hill earthquake. The 1984 Morgan Hill quake magnitude 6.2 was indeed the last big temblor on the Calaveras fault. Other mid-sized events include a magnitude 5.4 quake near Alum Rock, San Jose in 2007, and a 1979 event near Coyote Lake. By comparison, this swarm's largest temblor was only magnitude 3.8, roughly 200 times weaker in energy than a magnitude 6, and all others were smaller. These are benign rattles by Bay Area standards, indicating only very localized slips. Their real significance lies in what they reveal about underground stress changes and fluid pressures, not in any imminent danger of a big quake. Historically, seismicity on the Calaveras fault shows that the southern half of its central segment has been more active than the north. In the past century, that southern portion produced the Morgan Hill event magnitude 6.2, April 1984, and another magnitude 6.0 quake in 1979 near Coyote Lake. Further north, near Milpitas and San Ramon, the largest event before 2025 was the Alum Rock quake magnitude 5.4 in October 2007, which ruptured southwards. A century earlier, 1 or 2 magnitude 6 class quakes struck the region as well. 1911 often reported about magnitude 6.0 to 6.5 near the Gilroy-Morgan Hill area. And even in the 1860s, an 1864 California quake of around magnitude 6 in the San Jose area, sometimes associated with the Calaveras fault system. In short, the fault is capable of powerful shakes on multi-decadal timescales, but they tend to be concentrated further south. No large ruptures have ever been documented right under San Ramon or Danville. Instead, this locale usually adjusts via many microquakes or slow creep. Indeed, seismic records show that the San Ramon Valley has a history of minor swarms. Geologists have catalogued swarms in this valley going back decades in 1970, 1976, 1990 Alamo, 2002 to 2003, San Ramon, 2015, San Ramon, Danville, and the present 2025 event. Many of these swarms were comprised of hundreds or even thousands of small tremors over days or weeks. They are thought to relieve strain diffusely in the complex fault zone rather than letting one big rupture accumulate. As one analysis puts it, the earthquakes in a swarm tend to migrate along various planes, possibly in response to fluid movement deep underground. Essentially, water or other fluids under high pressure can weaken patches of rock on intersecting faults, leading to a cascade of slippages. Alternatively, the underlying tectonic stress may simply find many weak spots to rupture, one after another. Either way, dozens of roughly similar small shocks mark the event. The recent Bay Area swarm fits this picture. All of the November 2025 quakes were located within a few kilometers of each other under the Calaveras fault zone by San Ramon Danville. Their hypocenters were at mid-crustal depths approximately 8 to 9 kilometers, consistent with the main brittle layer of the crust. The largest shocks, the magnitude 3.8 and 3.7, around 5:38 to 5:39 in the afternoon, Coordinated Universal Time. 10:38 to 10:39 in the morning, local occurred within seconds of each other, essentially a doublet burst of energy. Many smaller ones followed. Several around magnitude 3.0 occurred by 5:41 in the afternoon UTC, and then dozens of magnitude 2 and 1 temblors through the night and into early November 10th. The pattern, a tight cluster of quakes over a short time, clearly looks like a swarm. There was no single large earthquake that could be called the main shock. The ground jiggled in a series of hiccups. Such swarm behaviour suggests that the fault zone is adjusting to stress changes, perhaps as a new patch of rock slowly slipped or as fluids migrated. Because no major quake has occurred in that spot recently, the crust could be unloading a bit of accumulated shear. In addition, fault creep may have redistributed stress to a nearby locked patch, triggering repeated small quakes there. Alternatively, a small creeping patch itself could have accelerated briefly, breaking into successive little slides. Experts will analyse the seismic recordings and GPS measurements to see if any slow slip or geochemical anomaly accompanied this swarm. For now, the swarm appears to be a self-contained release. It began, produced dozens of quakes and then quieted without a dramatic conclusion. As the Berkeley scientists note, nobody can predict how this is going to play out. But if the past is any indication, these quakes could continue for months in a sporadic manner. It's literally a waiting game for scientists, though the prevailing hope is that these small ruptures are doing the fault's work of releasing stress, and so perhaps making the chances of a future large quake slightly lower in the short term. In technical terms, this swarm exemplifies how strain partitioning and fault complexity can govern seismicity. The Bay Area's crust is riddled with fault strands. The Calaveras runs roughly northwest-southeast. The Hayward crosses it, and the Mount Diablo thrust terminates near here. The regional plate motion Pacific, moving northwest, exerts both shear and compressive forces. As the ground moves, some of that motion is taken up by steady creep on parts of the fault, as in the southern Calaveras, while the rest loads locked patches, as in the northern Calaveras. When the locked parts finally slip, it may be in small bits or rarely in big ruptures. Swarms likely mark the scenario where many small patches slip incrementally, sometimes triggered by fluids or by stress transferred from nearby slip. In a very real sense, each of the little November temblors was a micro-rupture on some minor fault plane, or a tiny patch of the Calaveras fault. Collectively they might not grab headlines, nobody was hurt, nothing fell apart, but they reveal the underlying mechanics at play. It's worth emphasizing that nothing about this swarm suggests an imminent major earthquake on the order of magnitude 6 or higher. All things considered, the Calaveras fault central segment is already moving pretty quickly via creep, and has not been known to produce huge shocks in this area. The USGS working group earlier estimated only about an 11% chance of a magnitude 6.7 or larger on the entire Calaveras fault in the next 30 years, reflecting the belief that most strain that is already being shed slowly. The recent swarm, composed of moderate-sized shakes, seems to comport with that idea. The fault is unlocking in small steps rather than waiting to break suddenly. In fact, one way to look at swarms is that they might reduce stress on certain fault sections by creeping a bit, like gradually opening a valve rather than blowing a cap off. Nevertheless, scientists will continue to monitor the situation closely. Dense networks of seismometers and geodetic instruments can tell them if this swarm shows any unusual patterns, for example, migrating hypocenters, changing wave speeds which could hint at fluids, or evolving stress shadows. For now, the swarm has mostly subsided. By November 10th, only a trickle of minor aftershocks and unremarkable tremors were being detected, far fewer than in the peak activity of the previous day. In a nutshell, the San Ramon swarm of November 2025 was a geologically intriguing event. Dozens of minor quakes rattled along the Calaveras fault in a concentrated burst, at depths of about 9 kilometers, approximately 6 miles. The largest shocks were magnitude 3.8 and 3.7, far below what normally worries seismologists. Crucially, the swarm fits the pattern of previous swarms in the San Ramon Valley, a known hotspot for slow, multi-shock sequences. All available evidence points to a localized technical adjustment of the fault system, not a sign of a looming disaster. Geologists describe it as a stress transfer via a complex set of faults, where even groundwater or deep fluids might play a role in lubricating the tremors. In a sense, it's Earth's whisper in response to the relentless Pacific North America motion, reminding us that even minor faults have their own stories. Stay alert stay curious, and keep the energy rising. Don't forget to like, share and subscribe for more breaking seismic updates, and tap that hype icon to keep the momentum shaking.